So I wanted to give a little unsure of what to present, so I want to give a little overview of NCAR, if you're not familiar with our institute, and then just a project that I'm working on in support of climate monitoring. So next, please. So for those who are not familiar, NCAR is up in Boulder, Colorado. If you've ever seen the Mesa Lab, that building up on top, that's our building. We were founded in 1960, and we're sponsored by the National Science Foundation. So we get about half our support from the National Science Foundation to do fundamental research into atmospheric and oceanography. Next, please. NCAR is comprised of 4 main laboratories. We have the Earth Systems Laboratory, the Computational Information. Sciences. Earth Systems Lab and computational facilities are focused on climate modeling, developing new climate techniques, understand the atmosphere and the ocean coupling, and then taking that information, put it into the global climate models. And the global climate models, of course, takes a lot of computing, and as computing grows, we go to finer and finer resolution. We can start resolving these fine-scale motions in the atmosphere where we weren't able to understand even 10, 15 years ago. So it's really improved with the technology today. So next, please. Yep. So we also have great research instrumentation. So we have a Gulfstream 5, a C-130 research aircraft that flies around the world and does global monitoring. Everywhere from air chemistry to atmospheric conditions. Recently, to look at climate change, they went from basically the Arctic to the Antarctic, flying north and south, which has never been done before, going all these great locations from very cold regions to the tropics and then all in between. We also do advanced weather radar research, looking at severe storms and how severe storms impact society. And then we have atmospheric monitoring networks that we put around the world for research. Okay, next. So this is where I come in. I'm actually in the Research Applications Laboratory. So we take that technology, we build applications to meet societal needs. That's our mission in our laboratory. So I'm a little more passionate about that. That's really what I like to do. So we look at things, we take that information, those forecasts, we look at extreme events forecasting. This is an example of the flood in 2013 in the Front Range. We do flood predictions. We take that information, bring it into flood prediction models to see where we're going to have human impacts, try to get out of harm's way. We do a lot of renewable energy planning now to take these climate models, the weather forecast models, try to optimize renewable energy generation. Aviation hazard, that's where we got our feet on the ground in terms of weather, looking for aviation hazards. So when you're flying across the U.S., across the world, a lot of the forecasts and the products came out of our laboratory to keep the aircraft safe. And then lastly is regional adaptation to climate change. So we take the global climate models and we drill it down and try to develop protocols and I'm trying to think of the right word, policy for regional governments to adapt, so they can, say for agriculture, adapt what kind of crops they can grow for a changing climate. So just a few slides on climate modeling. So NCAR is at the forefront of climate change research. We've developed the community Earth system model, which is one of the primary models that are used to look at climate change, these long-range climate predictions. Our model is one of the primary ones that are used. What's really cool about NCAR is we try to make everything public. So it's a community model to look at both past, present, and future climate. So you can go there today, you can download this model, you can install it on a system of your own, you can do your own climate modeling. Or you can take the output, and it's a vast amount of data. That's the promise. It's a large amount of data to try to disseminate. You can go there and you can come up with your own applications and look at your specific needs. It's all open source for the community. And so with that, we've been involved in all the climate change assessment studies, IPCC, and recently the coupled model intercomparison project, or CMIP. Next, please. So again, going back to our laboratory, we look at, again, climate change applications, on a regional adaptation to climate change. Our whole goal is to promote sustainability, reduce vulnerability to climate change for agriculture, water, health, urban environments, energy, ecosystems. So we're trying to make usable science for decision making. So how do we impact societal impacts for extremes, provide climate services so local governments can make their own decisions with the information they have that is relevant to them, not just the global climate, but drill down to their region. Next, please. So as I mentioned in my introduction, climate change research, the accuracy of these climate change predictions, and if you look at a spread of climate models, it's quite large. Most of this due is the lack of information that we have about the atmosphere. So we really have a lack of observation. So this is a nice map of surface observations around the world. You can kind of see the density and the number of years of record. You see over the U.S., we're well sampled. Even though we're still not really well sampled, it looks great. It's like everybody has a weather station in their backyard, but not really. We're still on the order of 10, 15 miles or even more per station, which is really not enough to really understand the atmosphere. But then you get to South America, Africa, which is where I'm working at now, Asia. There's almost no observations. So a model is only as good as its observations. So if there's no data, then the accuracy of these models are somewhat limited. So one thing that I'm working on is developing low-cost innovative technologies. And one of the reasons is commercial sensors. Why there's no observations in these regions? Commercial sensors are expensive to these countries. They can't afford a $20,000 weather station. And then they can't maintain it. They just don't have the resources for it. So we've come up with, my project is to try to develop this low-cost solution using Internet of Things. So we're using 3D printer technology, micro-weather sensors, single-board computers, very small, inexpensive technology that provides accurate information in these regions. And they're all streamed live back to here, actually. So next, please.